Hello again, friends. We are back today to talk about probability. So we started yesterday, or whenever you happen to watch that, talking about an intro to probability. And today we're going to talk specifically about one kind of probability, and it's called experimental probability. So we have experimental probability, and we also have theoretical probability. And the difference between these, so experimental probability is what does happen, like when you perform an experiment, or when you flip a coin 100,000 times, like how many times you land on heads. That's experimental probability. Theoretical probability is what should happen. So like if you've ever heard somebody say, okay, so in theory, what should happen? Like that's what's meant by theoretical probability. So in theory, when you flip a coin, it should be 50-50 chance that you land on heads or tails. But in practice or in experiment, when you flip a coin, you can flip a coin 10 times and land on heads every single time. And so you're sort of defying theoretical probability by your experimental probability. So today we're just talking experimental probability. And the way you find that out is this little formula right here. So the number of times that the event occurs, like in trial, right? So when you try it, and then over the number of trials. So how many times did you do it? Like how many times did you flip that coin? And then how many times did it land on heads? So how many times did it land on heads over how many times you actually flipped the coin, okay? All right, so the first problem here is we have an experiment consists of spinning a spinner. Use the results in the table to find the experimental probability of the event. Okay, so we want to know how many times in this experiment the spinner landed on orange. Well, this right here is how many times it landed on orange. So it landed 10 times. So it's going to be 10 over the number of trials. So you have to total up all of these. So 15 plus 10, that's 25, plus another 15 here, that's 40. So 10 over 40. And I would much prefer you to, and I know Delta Math would as well, reduce this to 1/4. Sometimes we also look for it as a decimal, 0.25. Sometimes we look for it as a percent. So all of these are okay, and it sort of depends on, for your assignment, what Delta Math asks. Now, this is a really nice percentage, a nice decimal. They're not all like that. And so usually a fraction is best, or maybe a decimal, like rounded to the nearest, 100th or what have you. But make sure you just pay attention to how they're asking the question and how they want you to answer. Okay, so if it says rounded to the nearest percent, then put it in percent form. If it says as a fraction, or if it says as it's round to the nearest, 100th of a place, or what have you, nearest 100th. Okay, next one, number 2 here. Another experiment consists of spinning a spinner. Use results in the table. So in this spinner lands on red is what we're looking for. So I have that happen 7 times. So red over the number of trials, so total number here. So red is 7, total number, this is 15 plus 5 is 20. So this is one of those ones I was talking about, like it's not going to be a super great decimal, but if you take, so you have 7 over 20, you could leave it like that because that's in lowest terms, or you could get it as a decimal, I guess it is 0.35. And then of course as a percent, it'd be 35%. Oh, I'm sorry, I didn't even realize that there was other ones here. Okay, so going back, let's delineate here. So going back to this problem, so 2 goes with this table. So it says the spinner does not land on green. Well, it lands on green 15 times out of 40. So green is 15 out of 40. So not green, because you're either green or not green. So you could do one of 2 things. You could add up orange and purple and pink. So 10 plus 8 is 28 plus 7 is I'm sorry, 10 plus 8 is 18, plus 7 is 25. So you can either have 25, and I paused because I'm like, wait, I'm going to get 35. It's supposed to be 25. All right, so you have 25 over 40, and you can get those by adding those together. Or, since you're either green or not green, and you have 40 total, this not green has to be 40 minus whatever green is. So 40 minus 15 would also give you 25. So you can get that either way. And that is super important to know because sometimes it's way easier to subtract than it is to add. Like this is only 3 numbers here. But if it was like, Scrabble letters and you have, 26 letters in the alphabet and there's a whole bunch of each one, then that's a little bit more obnoxious to add all of them up. And it's just way easier to subtract from the total. Now, this is definitely not in lowest terms. So you'll want to do that. And so if you just, each of these is divisible by 5. So we have 5 over 8. You could also, this is 0.625. So you'd probably round it to 0.63 or 63%, depending on what it's asking. And I would just go with whatever your choice was here, use the same choice here. So if it was 1/4, use 5/8. If it was 0.25, use, 0.63. If it was 25%, use 63%, right? So have kind of the same units, so to speak. All right, going back to this problem here. So this table, spinner does not land on red. Again, it lands on red 7 times out of 20. So 20 minus 7 is 13. So it would not land on red 13 out of 20 times. And that is in lowest terms. So you can get a decimal out of that. So you'd have 65 or 0.65 or 65%. That you can also get just from subtracting, right? Because this 0.35, if you take 1.00 minus 0.35, you get 0.65. If you take 100% minus 35, you get 65%. So you can subtract it anyway, whether it's, fractions or decimals or percentages. So make sure you do that. All right, roll 2 fair die at the same time. Sample space of the sum of 2 die. So we kind of did this on the sample space one yesterday. So the sum of 2 die, the lowest possible I could have is if they both land on 1. So 1 plus 1 would be 2. And then I have every single possibility, 8, 9, 10, 11, up to if they both land on 6, so 12. That's my sample space. Just a little review from yesterday. You're like, well, how do I know what I roll? Oh, look at here. I have dice. All right. So I'm going to do this 10 times. And I'm going to, oh my gosh, look at that. I got 2. I'm going to record my outcome. So my first roll was a 2. Okay. My second roll was a 4. I rolled 2 doubles. If I roll one more set of doubles, if I was playing Monopoly, I would go to jail. Oh, whew, good thing. All right. Number 3 is a 4. My 4th trial is 11. My 5th trial is 8. My 6th trial, you can't see that, but there you go, just so you know I'm not lying, is 7. 7, by the way, is the most popular number to roll. You know why? Because you have the most amount of combinations of it. You have 1 and 6 or 6 and 1, and then 2 and 5 or 5 and 2. And 3 and 4 or 4 and 3. So there you go. You have the most amount of that. Sorry, you can't see that when it went off, but there's another 4. I got a 10. I've rolled a ton of doubles. I feel like these dice are weighted for doubles. They're not. But. And then I have a 3 and a 1, so I have 4. Okay. So now I take this for my little experiment here. And I say, okay, the probability of rolling a sum of 5. So I look at all my outcomes, and I don't have a 5. So this is 0 out of 10. And remember, because it's the number of times that it occurs over the number of trials, right? So I rolled the die 10 times. That's like, so my denominator first before I reduce, and all of these is going to be over 10. So 0 over 10, of course, is just 0. So 0%. But this right here, and I'm glad that this happened because this is the difference between experimental and theoretical probability. Because remember yesterday when we talked about outcomes and how a 0% chance would be impossible. Well, it's not impossible to rule a sum of 5. It's very possible. I can have a 1 and a 4, or a 2 and a 3, or a 4 and a 1 and a 3 and a 2, right? So there's 4 different ways to do it. But it is impossible, and it would look impossible in this one because it didn't happen. So that's really, again, the huge difference between theoretical probability and experimental probability. Experimental probability means I did it 10 times, I didn't get any, so it's 0. But theoretical probability would be, however many ways it can happen over the amount of ways, like the amount of possible outcomes. We'll get more into that tomorrow. All right, probability of rolling a 12. I didn't roll a 12 in here either. So that again is a 0 out of 10 or a 0 or a 0%. Probability of rolling a sum less than 10. So anything less than 10. So there's 1, 2, 3, 4, 5, 6, 7, 8. So I only rolled over 10, or 10 or over, I should say, twice. So this is 8 out of 10. But again, you have to reduce that. So if you take a 2 out of each, it's 4/5, or 0.8 or 80%. And again, it would just be, you don't have to give all these answers. One of those is fine. You just have to make sure that you're following what you're being asked for. So as a percent, what is it? As a decimal, what is it? Etc. Probability, of rolling an even sum. So even numbers, of course, divisible by 2, 2, 4, 6, 8, 10, etc. So that was all of them actually except for 11, right? That was my only odd number, was right here. So that was 9 out of 10, and that is reduced. So 0.9 or 90%. But again, remember, it's not 90% for sure that you're going to roll an even sum. That is just what so happened to occur when we did the trials. All right. Now, the other thing that we have to do with experimental probability is called making predictions with data. So a lot of quality control is done using probability, right? So you'll test a sample of goods in your factory or what have you, and you'll see how many of them have flaws. And then you'll use that number to do what's called extrapolate. It's a big word. Extrapolate. And to extrapolate means to take the data that you got from your sample and kind of push it out and say, okay, here's what we can expect for all of our products. If we found that 90% of them were defect free when we pulled our sample and we got a decent sample, then we can assume that 90% of all of our products are going to be defect free. And it doesn't always work that way, but it's the easiest way to do it, particularly if you can't sample all of your products. All right, so making predictions with data. First, you find the probability from what's given to you. So this will always be like a possibility for you to do. And then you take that, you write it as a decimal rounded to the nearest hundredth. And then you multiply that probability being this one, by the number in the next sample. And usually that's like the total number of goods, and not of the sample, right? So it'll make more sense when we do a problem like this. But the reason why you write as a decimal rounded to the nearest hundredth is because you do have to multiply it. So, I suppose you can do it as a fraction, but most people don't like multiplying fractions. But you definitely don't want to write it as a percentage, because you don't want to accidentally multiply 96 by something rather than 0.96. All right, let's do a couple of these. So a manufacturer inspects 500 strollers and finds that 498 of them have no defects. What is the experimental probability that a stroller chosen at random has no defects? So one of these. So you take these two numbers. So I want no defects over the total, right? So the ones that have no defects, that's 498 over my total of 500. And if you're ever wondering, like, am I writing the correct thing on top? Well, remember, your probability has to be between 0 and 1. The only way it's between 0 and 1 is if your numerator is smaller or equal to your denominator. So if you have 500 over 498, you'll get a probability over 1, which will be a probability over 100%. That won't make sense. So always, always, always do the smaller number over the bigger number. Or again, they could be the exact same if it's 100%. All right, so if I do 498 divided by 500 in my calculator, I get 0.996. And I have to fly in the face already of number 2, because if I do round that to the nearest hundredth, I'll actually round it to 100%. So I don't want to do that. So I'm just going to keep it the way it is. Okay, so pretend I didn't say number 2. So 0.996, I use that, and I multiply this probability, this 0.996, by the number in the next sample. So this says the manufacturer shipped 3,500 strollers to a distribution center. Predict the number of strollers that are likely to have no defects. Well, if 0.996 of them didn't have defects, then I'm going to use that same number, 0.996, and I'm going to multiply that by the 3,500 that were shipped out, 0.996, and say that 3,486 of them will have no defects. And then again, like probably, right? Because this is a prediction. We don't actually know if they have defects or not. Okay, next one, same exact thing, except not strollers. Now we're talking about toothbrush motors of electric toothbrushes. Very important stuff here. So inspect 1,500 electric toothbrush motors, find 1,497 of them have no defects. What's the experimental probability the motor chosen at random has no defects? So again, same thing. I take the smaller number, so 1,497 over 1,500. I'm going to do that in my calculator. Probably hear me pushing my buttons. And I get 0.998. So again, yeah, let's just go back up here and be, we're just going to totally ignore that. I mean, you do want to write it in decimal form. Okay, but if it's going to round to the point where you get 100%, like this one also would, don't do that. Okay, because you would just end up with the same number you started with. All right, 35,000 motors in a warehouse. What do we think the number of motors that are likely to have no defects? So again, this is the probability of having no defects. So we multiply these two numbers together. So 0.998 times 35,000. That's a lot of electric toothbrushes. 0.998. Okay. 34,930 should be anyway, defect free. All right, so those are our notes for today. And what I have you doing here for experimental probability is, if you choose, you can find a few different things. So a dice, so just one dice, a deck of cards, and a coin. If you don't have those things, you can either, choose to do something else, whether you put 5 different colored pens in a bag and you don't look and you pick one out, or, whatever. Like, find something that has different outcomes and kind of make your own experiment. So what you want to do, though, you just have to make sure you blindly pick each time, especially with the cards. The coin toss and die roll, you can't blindly pick. You just roll the die or toss the coin, right? But you do it the same way we did the dice roll one on the other one. So, for instance, we have a die roll here, and I put the experimental probability formula up here for you. So in attempt 1, my outcome was a 1. In attempt 2, my outcome was a 6. In attempt 3, it was a 2. Right? So that's kind of, you go through the whole thing and do it that way. I wonder if I have any coins near me. Oh, I do! How exciting is this? Okay. So then, a coin toss one, I would go, that's tails. I flip it again, and I get tails again. Flip it again, and I finally land on heads. Right, and so you just go all the way through on that. And then if you have a deck of cards, so you have to, you're going to list the color. So it's either red or black. And the number or face. So numbers go 2 through 10. And then you have some special cards. So your face cards, if you don't know this, are Jack, Queen, King. And then you also have a special card called an ace, which is either high or low depending on, what game you're playing. But it's sometimes a 1, sometimes an 11. And so when you pick a card, all right, talk amongst yourself for a second. I'm going to go grab a card because I know I have a deck of cards like pretty close to where I'm sitting. So I will be right back and we'll become card sharks. All right, I'm back. Told you that wouldn't be too long. So here's my deck of cards. Right, McLaren, Port Huron, Hospital. So I'm going to shuffle them up. And then I'm just going to pick one. And it's a 5 of clubs. I suppose you can, if you want to, list the actual suit, right? So you have hearts, diamonds, clubs, and spades. But I can just do 5B right now. Because if you look at the experimental probability I'm looking for, it's for a face card. So that's all. There's a 5 of diamonds, so it's a 5 red. There's a 4 red. If I just shuffle these up again and do. So also, though, I will say what you should be doing is not what I'm doing. You should be replacing them every time and reshuffling. So make sure you do that. Oh, I got a king. So king of hearts, a red king. So that would be a face card. So right now, my experimental probability of face card is 1 over 1, 2, 3, 4, 5. So there you go. All right. So that's how you do that if you decide to do probability experiments today. Okie dokie. Okie dokie. Well, you guys have just a fabulous day. And I will see you tomorrow.